Hello, Fat Mama Physics signing back on. This is part 2, a video on circular motion, showing how to apply some circular motion equations to orbits of satellites, objects. We did this part 1 back here, showing how total energy of your orbiting satellite has this very interesting relationship between its potential energy and kinetic energy. In this second video, we're going to show us how we can apply that. So some of the equations I will be using and showing us will directly come from the previous video. If you want to go check it out, you can, but I'm not going to spend time in this video going over how I got those equations anymore. It will just be pure application. Okay, so without further ado, let's begin. We have a 4,500 kilogram satellite, okay, which is in geosynchronous orbit. We're going to talk about that word in a moment. Calculate the total energy of the satellite. Answers given to us. And all of the other questions below. How to looking at total energy. Okay. To show us geosynchronous orbit, here I have a ball. This is one of my kids' basketball toys. And I'm just going to put a sticker, Fat Tiger, on this ball. Okay. Pretend this is where we live. Okay. Not sticking very well because it's been used. Okay, so imagine this is where we are. A geosynchronous orbit looks like this. Imagine I have a satellite, which is this flash drive that I have here. It's an office, of course. These are things we find. And since the Earth rotates around its axis, okay, notice how this tiger is rotating away from you, or the sticker is rotating from you. The satellite would go like this. It would always be directly above that tiger or that sticker, even as the Earth is rotating. Okay, so it is always above that spot. Okay, which means that in order for this satellite to make one complete orbit around the Earth, we know its orbital period, and its orbital period has to be 24 hours, which is one day it takes for the Earth to make one complete rotation around its axis. Okay, so that tells us that the period T is 24 hours. Okay. Whew. All right. Next up, that's an important piece of information. Total energy we obtained from the previous video, which we now know is negative, not just G, but negative 1/2 big G, big M, small m over R, in which big M is the mass of the Earth. And this is something you can probably obtain from your formula sheet or anything similar to that. It is a very big number. Okay. You also know that small m is the mass of the satellite. R is the orbital radius. Now, the geosynchronous orbit tells us our orbital period, but it doesn't tell us our orbital radius, which is annoying, means we have to try to find it. Now, I'll do this one over here. Now, we go back to the basic idea again. Always start with a free body diagram, free body diagram. No matter how little number of forces you have, but it shows us that the force pointing towards the center of the circle is the force due to gravity. And that's the one that's contributing to your centripetal force, or your F net, towards the center of the circle. Okay? Which means we're going to have centripetal force is m times centripetal acceleration, v squared over r. And force due to gravity is big G, big M, small m over r squared. Aha, a few things cancel. We have m's goes away, independent of mass, and one of the r's go away. And we also know that to get the orbital, looks like we don't have orbital speed either, but we can use orbital period, to get us orbital speed. Don't forget that I'm using all these little spaces over here, so let's divide the page like this. V, or orbital speed, is also 2 pi r orbital radius over orbital period t. After we put this v in there, we're going to have 2 pi r over period all squared. Okay, this is equal to big G, big M over R. Okay, all those things over there here canceled. All of these things over here canceled. So if we just work this out, we have 4 pi squared R squared over T squared. I'm assuming we are all very versed in our algebra, over R. Okay. Hey, look, there's a few things that can combine, namely this R over here. So if I multiply R on both sides of the equation, okay, I'm just going to get something that looks like this. Running out of space. Okay, 4 pi squared, now R squared, but R cubed, over period squared. This is equal to big G and big M. What we can do is we can rearrange this, okay, and you know what? I'm just going to move all of this to the other side now. What we want here is we want the orbital radius, okay? Now, to solve for the orbital radius, we'll have to rearrange this equation and move a couple things to the other side. Namely, we have to divide the 4 pi squared down here onto the other side, so that gets rid of this. We also need to multiply both sides by the period squared, which gets rid of this one down here. And we're left with this annoying R to the cubed is equal to big G, big M, period squared over 4 pi squared. The last step is very annoying because to get rid of the cubed on the R, we would have to take the cube root. Okay, we have to take the cube root of both sides of the equation. Now, there's a little trick you can do. You can take, if you take the cube root, this is equivalent to you taking everything on the other side to the power of 1 over 3. Did you know that? Because, you know, if you take the square root, this is like taking something to the power of a half. So if you're taking something to the square root, if you're taking something to the cube root, will be to the power 1 over 3. The fourth root and the fifth root, those you can do as well. Okay, but anyhow, in the calculator, that's what I would do. Let's put this in our calculator. G, which is 6.67, 67, times 10 to the power of -11, 711. Mass of the Earth, 5.98 times 10 to the power of 24. And the period is going to be 24. It's technically 4 minutes less than 24 hours, but let's round it up to 24 hours times 3,600 seconds per hour. Don't forget to square this. Divide it all over 4 pi squared. And ultimately, we take all of these to the cube root. So after I get this, I get 4.225, of course, times 10 to the power of 7 meters. Okay, so that is our orbital radius. We are going to take that and plug it back into our equation. Okay, so I'll do this in the middle of the page. It looks like all the space I have left. This is 1/2, again, G, substituting in G, mass of the Earth, mass of the satellite, which is provided in the question, and that should give us all of what we need. And the radius is 4.225, and I'll try to save as many digits in between steps as possible. And I get, I forgot the negative sign, negative 2.124 ... times 10 to the power of 10, okay, which rounds up to about negative 2.1 times 10 to the power of 10 joules. Yay, we got the answer. Okay, so now we're going to do exactly the same thing, but below we want the total energy of the same satellite at triple the orbital radius as the one in A. That's not too bad because all we have to do is plug in exactly the same thing, except our new orbital radius, I'll put this R2, is going to be 3 times this number, 4.225. Don't forget to save all of our digits, times 10 to the power of 7. And we're going to get 1.2675 times 10 to the power of 8, it seems like, meters. Okay, don't forget units. So we calculated total energy. This is not that exciting anymore because we already did everything pretty much the same thing as before, but we have our new total energy. I'm going to call this 2, R2. This is at the second location. So after putting everything in, we get, oh, and I made a blunder earlier. I forgot to include this 1/2 over here. So easy to leave out, right? So, it's been a while since I've done videos. So, sometimes, when your mind is focusing on how badly your computer's running and the lighting in the room and everything, and you forget a few things. So I apologize for that. If it were in the classroom, I would have lost the candy already. But anyhow, you caught my mistake maybe earlier than I did. Aha! So congrats if you did. You were paying attention. So after putting in the 1/2, we do get this one in the answer key, negative 7.1 times 10 to the power of, and on my calculator it says 9. Okay. And notice it is still negative, which makes sense because, of course, this is another video, but potential energy is supposed to be, we count that as negative at infinity. So anything below that will have a negative value. Actually, this appears later on, so let me save that for then. Okay, so finally, got a total energy of the same satellite at triple the orbital radius. So now what we're going to do is we're going to find the work needed to put this satellite in A to triple its orbital radius. Now, in order to do that, it's actually, if you think about it, it's going to take a lot of work. Not only have to put the satellite at, you would have to put this at further distance, which means you have to put energy to overcome the gravitational potential energy required. But at the same time, the satellite doesn't need to go as fast the further away it is from your planet. Okay, if you think about your satellite being further away, it doesn't need to go as fast to stay in orbit because there's less of a pull, meaning you have less gravitational field strength to fight in order to stay in that orbit. So yes, you do need enough work to get you further away from the gravitational pull, but also some of that you don't need as much kinetic energy. In fact, you need much less. So there has to be a balance. So in order to actually figure this out, it is much easier to go back to the definition of work, which is the change in energy. And namely, for our sake, we're looking at the total energy of our satellites, which means if we want to take the total energy at point 2 minus the total energy at point 1. Okay, so finding that difference is going to help us. Hey, and guess what? We already calculated those in our previous questions. So all we have to do is just to go ahead and do the subtraction. We found total energy in part 2 in question B. So that's going to be negative 7.1 times 10 to the power of 9 joules. Subtract total energy at part 1, which is when it was in geosynchronous orbit, negative 2.1 times 10 to the power of 10 joules. Okay. And then we're going to get, so we get here 1.39 times 10 to the power of 10, which I've rounded up to 1.4 times 10 to the power of 10 joules. Okay, so, and hey, look, after we do the subtraction, we get a positive value. This shows that this makes sense because you need to do work to get your satellite to a higher orbit. Okay, now we're ready for D, the minimum work needed. Minimum work needed to get satellite in A completely away from the gravitational influence of Earth. Now, when we say completely away from the gravitational influence of Earth, this means that we're going to go far, very far away until we reach infinity. Okay, infinity is a very interesting place. Now, in the context of orbits and in this unit, because a lot of things there's different things that we'll expect at infinity. The reason why it says minimum work, I'll get to that in a second. Because let's first start off with the amount work needed. We know work needed is the change in the total energy. Now, we already know the total energy in A. Okay, that's the geosynchronous orbit one. But in order to know the change in total energy, we need the total energy at infinity. Okay, at infinity, let's reason out what would be the potential energy and the kinetic energy. Now, first things first, let's start off with the minimum work needed. Now, let's think about the kinetic energy at infinity. Your object could be moving, it could not be moving. It doesn't necessarily have to move. As long as it gets there, then it's okay. There's no way for it to be in orbit in the first place, because if you are at infinity, there is no way for your object to necessarily be in orbit, because FG, your radius, would be close to infinity, which would make this closer to 0, and therefore your object no longer in orbit. But your object not being in orbit, it doesn't even have to be moving at all. Why spend that extra energy anyways? And this is where the minimum comes in. So this would be 0 joules. For potential energy, well, let's go back to the very definition of potential energy. EP is equal to negative big G, big M, small m over R. Well, if R reaches infinity, EP is still negative, but it's going to become a smaller negative and a smaller negative and a smaller negative until it reaches 0. So EP is also going to be 0 as well. That gives us our total energy as 0 joules. So our change in total energy in this case would be your final minus your initial, okay? Our final, which is at infinity, is 0 joules. Minus the amount that is in A, which is, what was our answer? Negative 2.1, right? Negative 2.1 times 10 to the power of 10 joules. And if you subtract a negative, this will just become positive. Positive 2.1 times 10 to the power of 10 joules. And this kind of makes sense. You would have to fight your orbit, get out of the gravitational influence of your planet, which is Earth, in order to get there. So that's the amount of energy you would need to get to infinity. And once you're at infinity, well, let's see. That's what E is going to talk about. If this satellite was released from far, 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 far away, infinity and beyond, from rest. Oh, hey, from rest. From rest means EK is equal to 0 joules, because it's not moving. Velocity or speed is 0. What speed would it impact the surface of the Earth? Basically, you have a satellite, it's just going to kind of unwind itself, and, at one point, it's going to crash onto the Earth. It's like two objects that will eventually meet each other in the end. So gravitational attraction is always attractive, never repulsive. Ha ha ha. So anyhow, what that means is, again, we're going to, here we have an energy conservation. And hey, we're bringing back stuff we learned before, which means the total energy, all of the energy it has in infinity will get converted into other forms of energy as it gets closer and closer to Earth. Okay, so E total at infinity is going to be equal to the E total, okay, when it crash lands to Earth. Okay, so I'm going to write here maybe C for or S for surface here, S, okay, surface of the Earth. Well, we already know that the E total at infinity is 0. 0 joules as determined from number D. So that's 0 joules. Equaling to the total energy at S on the surface. Okay, well, on the surface, we're going to have potential energy on the surface and kinetic energy on the surface. And we are trying to find the speed, which is really us trying to find out the kinetic energy. Well, if we take a look here, we have the potential energy is going to be negative big G, big M, small m over R. And this is going to be the rate. This will be the distance from the surface of the Earth to its core, from its center, really just the radius of the Earth, because that's where it's going to crash land. Okay. Plus the kinetic energy of your object, 1/2 mv squared. You're like, ooh, why did you switch back to this one? Well, we're trying to find the speed of impact. We're not trying to find the orbital speed or anything else anymore. So we're just trying to find this v right here. And if we kind of rearrange this a little bit, we'll notice that the masses will cancel out. And we can go ahead and even rearrange this equation to solve for v itself. To solve for v itself, we're going to have to move parts of this to the other side. And in fact, I could move this big chunk over to the other side, which is going to make that positive. I also have the other side, which is 1/2 v squared. And if I solve for v by multiplying both sides by 2, then I am going to get, I'm going to have to square root both sides. This is kind of looking like the v escape, right? Like the escape velocity. It's almost like the opposite of escape velocity because you're crash landing back in a sense. 2 big G, big M over surface of the Earth or radius of the Earth, okay? And after we put everything in, we are going to get 1.1 times 10 to the power of 4 meters per second. So I checked again with the calculator, and hey, this would be exactly the same value as the escape velocity if you were at the surface of the Earth. Okay, so, and the other thing I could do with these type of questions is notice how we have conservation of energy. Instead of saying we release the satellite from a very far away distance, we can say what happens if the satellite loses power when it's in orbit. As it loses power, or if or something hit it, or not necessarily losing power, but let's say if this satellite redirected itself so that it will, fall back to the Earth or crash land on the Earth, then what would be the final speed before it hits the surface, kind of thing. So instead of this total energy being the total energy at infinity, it would be the total energy of your satellite that is in orbit. So it would be a different value, but it would be the same idea. You're using conservation of energy to assess how all of that energy will get converted into kinetic energy as your object loses potential energy, as it becomes more negative, and as your kinetic energy increases for us to find the final speed before a crash lands. So there's many ways we can ask this last question too. But otherwise, this is kind of the how we can take some of the things we learned in the previous video, and in calculating the energies at different orbits, and most importantly, looking at how work is used to get your satellite to a higher orbit, and also what kind of energy is that you're getting back if your object falls from a higher orbit to a lower orbit, or even worse, from infinity back down to the surface of the Earth. So there's many ways how we can look at the change in energy in those cases. Otherwise, hopefully you got something out of this video. Apologize for the messy writing. I'll have to actually write vertically like this, so that's why, But otherwise, thank you for listening to this video, and Fat Mama Physics signing out.